Okay, thanks so much for having me. So this title kind of says it all. This is going to be a more applied talk. I am a medical research applied statistician, so I'm just telling you that up front. We've heard a lot of wonderful talks about people developing packages. I'm going to be talking to you today about using a package that's out there in a slightly different way and hopefully expanding its uses a little bit, okay? So just bear with me. Okay, so what I'm going to do is talk about the motivation, sort of what led me to this method. An introduction to Bayesian Hierarchical Modelling. Now, I realize there's actually a tutorial on Friday on the topic, so hopefully this is a little bit of a warm-up for those attending. A proof of concept, so basically this is me trying out this package and seeing how it works and if it's good for me. And then finish off with some simulation studies where hopefully I'm extending what we can do with this package, okay? Right, so the motivation. Okay, so I don't need to tell anybody in this room that pooling has its drawbacks, right? But when you work in pharma companies and you're trying to get them to do anything Bayesian or a new method, you have to convince them, right? You have to say that this is going to be better than what we're doing. And the context that we had here is we had a clinical trial, right, that had some kind of strong treatment effect, but it was in a subgroup. And the idea was we wanted to borrow information from another historical study that was done within the company and just to hopefully improve the precision of it, okay? So just through, feasibility stage, I did a literature review, identified BHM as a key method for this. But just to note, BHM is really traditionally used for scenarios where you have sort of many clusters with small numbers. So for instance, in cancer, it's often used for basket trials, okay? So there was a simulation paper done by Austin in 2010, which looked at what happens with the variance components and sort of bias when you have less clusters but more people in your clusters. But I think we had to convince ourselves and our stakeholders that this method could be used in a setting with two clusters. So anyhow, that's kind of the main motivation. All right, so a lot of you will know this, so bear with me, but just as a reminder, BHM is a dynamic borrowing method. It allows the borrowing of the strength of information from a historical trial into a trial of interest to help estimate the treatment effect. So, of course, you can have many different types of clusters, but we were interested in two groups here for our context. And basically, it's hierarchical in that you can place an overarching population on top of your two different trial of interest populations. And really what you're assuming is that the parameters from your two trial of interest populations are random draws from that overarching population. So as I said, you could have many clusters, and the main thing that we were interested in was the impact of a specific treatment on survival, very simply, okay? So it's dynamic borrowing in that it borrows most when the clinical trial of data are in agreement with the historical data and borrows least when they're not in agreement. And a BHM has 3 different layers, and you have to estimate parameters for those 3 different layers, okay? So the first layer is sort of within the layers, or within that overarching, or we call the global population, and the trial of interest populations. Okay, within that you sort of have a global intercept, so that's going to be sort of your global survival, right, across that overarching population. You're going to have a global treatment effect, and you're going to have the variability that's within your groups across your mean survival model. The second layer is going to be the between layer, and what that models essentially is your group, the variability between your group specific, or in this case, your trial-specific intercept parameters, right? Because you're assuming the survival is going to be different for each of your different trial of interest populations. Now, to note, you can also assume that the treatment effect may be different for your 2 different trial of interest populations, right? But in this simplest case, what you're saying is, okay, the survival is different between your 2 different clusters. However, there's no reason to anticipate that the treatment's going to be more beneficial in one trial versus another, okay? But you can sort of relax those assumptions as you go. As this is a Bayesian model, the 3rd layer is your prior layer. And as I said, it's a dynamic borrowing method. So actually the variability parameter right here is what drives the borrowing, okay? So a BHM for survival data, you can actually formulate a hierarchical survival model through a hazard scale model. So as expected, you're going to have your baseline hazard. You're going to have your eta term as your linear predictor over here up on the right. As per usual, I are your individual patients, J are your groups or trials. And the first term of the linear predictor is sort of your global term, right? So it's going to include any parameter that's sort of global across that overarching population, as well as covariates that are sort of shared across that global population. The second term is going to be your group-specific parameters, as well as your group-specific covariates. So your group or trial-specific parameters or random effects are assumed to be normally distributed for a variance-covariance matrix, which is assumed to be unstructured. So we're making it quite flexible. And the above model includes the 3 layers, so within each trial in the first term, between trials in the second term, as well as our prior understanding of the broader overarching population. And again, that's across sort of your global parameters, right? That's not across your trial-specific parameters. So another very important thing for BHM is the phenomenon of shrinkage, okay? So what shrinkage means is that your group-specific local trends in the hierarchical model are shrunk or pulled towards the global trends, okay? So we know that there's drawbacks, obviously, to a completely pooled model because it ignores the fact that our data is grouped. And when you're using weakly informative priors, the posterior mean is roughly equal to the global mean. So hierarchical predictions are actually pulled or shrunk towards the global trends of their completely pooled model and away from the local trends. So it ends up being sort of in between both of these, okay? We know that shrinkage will increase as the number of observations on each group decreases. And this makes a lot of sense because we're going to rely a lot more on global trends to understand a group for which we have little data. Okay, so all the analyses going forward use the RSTAN-ARM package, specifically the survival extension, which was published by Bremen et al. In 2020, and the references are shown here. Okay, so the proof of concept. So this was basically taking the package out for a spin and seeing how it worked a little bit and learning a little bit about it, okay? The proof of concept purpose was to illustrate and re-estimate the published treatment effect using BHM. So this is much more of a classical data set that we would use for BHM in that you have 200 participants, you have 20 sites, you can call them sites, clusters, groups, whatever, and that the patients are split equally across the sites. We have some event time assumptions, including a fixed treatment effect. And what I wanted to do was fit 10 unadjusted models. The reason it's 10 models is that we looked at 5 different baseline hazard distributions. So parametric ones, you know, like exponential, Weibull, and Converse, as well as 2 cubic spline models. And the reason we get to 10 is for those 5, we fit 2 different models for each of those 5, where site or cluster, so that's always a random effect, right? So that could be site or trial or cluster or whatever, because again, you're assuming that the survival is going to be different for each of your clusters. But as I said before, you can treat treatment as just a fixed effect, so just that global parameter, right? You're again assuming that survival, that the treatment is unlikely to be just more beneficial in one cluster versus another, or you can say, actually, I do think that there's going to be a difference here, okay? And in that case, you can use treatment as well as a random effect. You're using weakly informative priors, right, which reflect general uncertainty across a range of sensible parameter values, right? So they're not weak, they're not strong, they're kind of a bit in the middle, okay? You're going to put them on all your global parameters as well as your auxiliary parameters, your baseline hazards. And as I said, the goal is to estimate the treatment effect in the overall population. Okay, so you look at, of course, model diagnostics and convergence checks should be the very first thing that you're checking always for your 10 models, but you're also looking at the difference in the cross-validated expected log predictive densities. Higher ELPD, the better, as you know. And so I list it in order from best to worst. And again, the convergence checks and model diagnostics are taken into account in this list. So just to show here, because I think it's always a good reminder that we actually have to really check our diagnostics. I know this is very simple and obvious to everybody, but I think it is worth reminding ourselves. You see the overlap in the chains in the density plots. You see the trace plots looking like fuzzy caterpillar shape, random. The autocorrelation plots all had a sharp drop. The R-hat values were all about 1, and your effective sample size ratio is above 0.1. So this tells us that the simulation is stable and convergence is indicated. You can also look then at your posterior results of your fixed effects parameter estimates and their credible intervals. And very reassuringly, when we look at the global treatment effect, we obtain the same hazard ratio as the literature. So then sort of suitably satisfied, we move on to the simulation studies. Okay, so again, this is using the same package. So as per usual, you simulate some data, you construct some models, you extract estimates, you run this a number of times, and you make some plots. So for this, I did 3 different simulation studies. Okay, so the very first one, again, this was to convince the stakeholders that, listen, let's not do completely pooled models, let's do something that's a little bit smarter here, okay? So what I wanted to do was to compare completely pooled frailty and BHM models to each other. So for that, I simulated data having a gamma frailty distribution, okay, with a specific treatment effect, 2 groups, because again, what we were interested in here was 2 groups, okay, of 100 participants each, having a specific censoring rate, and then ran everything 100 times. Okay, so the first thing to do, right, is what baseline hazard distribution are we going to use for our BHM models, right? What actually fits our data the best? So that's the first thing to check. And for that, the cubic V-spline was actually the best fit. So we moved along with that for the BHM models. Okay, so these are the results across 100 simulations. I appreciate the lines are a bit skinny, but I will walk you through. So we looked at coverage and bias here. We ran a completely pooled model. We ran a clustered survival model. Now that was a bit of a sense check because we did expect, based on our data, to fit the data quite well. And we ran 2 BHM models, one with non-informative priors and one with weakly informative priors. The black dots here are the estimated log hazard ratios. So that's what you get for each of the models. And obviously you're taking the average across all of them. And then the diamonds are the simulated log hazard ratio. So that's known, right? That's what we simulated the data on. So based on that, we can look at bias, okay? And then, of course, what you see here is the 95% credible intervals across all the simulations. So the first thing to note is that the 2 BHM models in the green and the red at the bottom compared very favorably with our clustered survival model, which was good to see. But in addition, you see there isn't really much of a difference in your treatment effect estimates, right, between the 2 BHM models, whether you have weakly informative priors or weak priors. But really the headline message for our stakeholders here was that if you compare the BHM models to the completely pooled model, you have much higher bias for the completely pooled model and much wider credible intervals, okay? So then the second simulation study. So now we get to more the meat of what we were actually trying to show here, right, for our own personal setting, right? So the historical study that we had was a phase 2 monotherapy study. Okay, and we wanted to borrow information into a phase 3 randomized study. So had to do some simulations. So I simulated data having an exponential data distribution, looked at a range of different treatment effects, right? So looked at 4 different treatment effects. I assumed, as you would assume, that, that the survival was going to be different for your phase 3 and your phase 2 study, okay? I had a specific censoring rate. I looked at a range of different sample sizes for the phase 3 study and the phase 2 study, okay? Because I wanted to see what happens with the different sizes, right, in your clusters if you only have 2. As expected, the phase 3 study is randomized 1-to-1 and ran everything 100 times. Okay, so this is the results. Okay, so in the legend here, you have, this is a simulated treatment effect, right? That's the 4 different scenarios here, all right? What you see along the x-axis here, that's all your different sample size scenarios, right? So that's combining each time the phase 3 and the phase 2. So that's all of them here. On the y-axis is the distance from the phase 3 hazard ratio. So what does this mean practically? So if your BHM models give you estimates that are identical to what you simulated your data on, right, for your treatment effects, we would expect the colored dots to be right on the dotted line, okay? However, as I mentioned, your phase 2 median survival is better than your phase 3 median survival. So when we borrow from it, we would expect to see that our effect estimates are pulled down, right? And indeed, we do see that kind of around the right-hand side of the plot. Where you don't see that is at the very beginning. So what's going on at the beginning? The beginning is this concept of shrinkage, right? So you only have, oops, sorry, too fast. You only have 50 participants in your your randomized phase 3 study, so 25 per arm. And what's happening is that you don't have a lot of information, so your estimates are actually being shrunk towards that global mean, okay? So then when we look at the coverage plots for this simulation study, we do get 100% coverage, but as you would expect, you're going to have much wider credible intervals the less numbers you have for each of your groups or clusters, okay? And so the credible intervals are shown here. You have your estimated hazard ratio for each of your models and your diamonds, and then what we have, what we simulated our data on here, okay? Simulation study is very much the same, except we looked at less numbers of treatment effects. We looked at less numbers of sample sizes for our phase 2 and phase 3. The only difference that we did here is that we wanted the survivals to be the same for both clusters. And the idea was to really get a chance to look at bias in that way, okay? And really sort of what you're seeing here is that sort of the more number of participants you have sort of across your clusters here, the least bias you have. And again, we have the phenomenon of shrinkage that's happening here. This plot tells you very much the same. Essentially, you also get the 100% coverage, but you see the much wider credible intervals across all your simulations here when you have less participants in your clusters. And so then to conclude, we identified BHM as a key method for the borrowing of information from a historical trial into a trial of interest. And simulation studies, completely pooled models are found to have higher bias and variance than BHM models in the first study. The use of uninformative or weakly informative priors did not really impact our estimates in the first study, but we can obviously do further work and extend this to stronger priors and so on. In the case of combining trials with different median survivals, you really need to have enough patients help estimate the treatment effect, but again, we need to look at further simulations. We had 100% coverage across all simulation studies, and we felt based on what we saw that this method could be an approach to consider in different contexts, especially sort of when you have less number of clusters, so it's a bit less of a traditional method. And that's it. Yeah.
Were you successful?
Yes. Yes. I was successful, and we're actually implementing this method, but it's proprietary data, so I can't actually show you the results, but I'm very happy to report that Daiichi is using BHM now in our department, so yes.
I'm curious a bit about what was decisive in persuading.
I think, to be honest, it was the first study, which to us is rather obvious. A completely pooled model are going to have sort of that higher bias. But I think if you're not a statistician, and especially these are sort of medical researchers, more biologists, they just need to see it. And we did it in so many simulations. We also had the computational issues with Stan, and I don't really blame. I know you're going to ask me if the effective sample size I was targeting and so on and so forth. But I think, sorry to point you out that way, but and just to say we had 10,000 iteration, 4 chains, blah, 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 and we had a small step size just to try to get the best convergence possible. So we set our adapt delta to being 0.99. But the main issue we had, frankly, is we don't have access to a good server. So we had sort of, because it had to be run on the company stuff, and we just didn't have the computational power. So I don't really blame the package here. I think the package is fantastic, but I think it's something that I think it's also helping the company realize that if we want to use fancier methods, we need better tools. So it's also been part of that approach. So it's been good for multiple reasons.
So when you say 100% coverage here, what were the intervals and how many things were you looking at? Because usually you expect coverage at the rate of the interval. So that would seem like too much coverage for
Yeah.
posterior. Like if you're looking at 90% intervals, you want 90% of them to cover, not 100%.
Yeah, we just kind of gave our results, to be honest, and we found that, our estimates were always kind of within kind of the full thing. So, But I
But
appreciate
how
what you're
wide
saying.
were your posterior intervals? Like what probability did they cover?
Can I get back to you on that?
Sure.
I need to look back. I ran this a few months ago, so I don't remember, to be honest.
So the other question I had, if there wasn't anybody else, is it looked like complete pooling had wider posterior intervals. Usually the complete pooling has narrower.
Yeah.
So is that because you were pooling things that were very inconsistent with each other? And therefore you needed to pull out a very wide interval to cover all the possibilities?
Again, can I get back to you on that? I don't know. I'd have to go back and look. Yeah. Sorry about that.
I think the answer is probably.
Yeah,
Probably,
but
yeah.
I don't want to guess.
Okay.
So I think it's just better to say up front. I ran this a few months ago, so I don't really remember. But.
Do we have more questions in the room?
This is a bit sort of separate, but you mentioned using RStan-ARM and specifically the survival branch. And I know RStan-ARM is on-prem, but I believe the survival branch isn't.
So it's from GitHub. So I had to
I was gonna
download.
ask if I've heard previously, especially in sort of medical research context, that can pose some difficulty. And I wonder if you
It
had-
did. It
Okay.
posed a lot of difficulties, but I have to say the developers were amazing. And I just went on the chat boards and I was like, this isn't installing, help. And so essentially, yeah, they were great. And essentially sort of what I needed to do was that, some of the advice was like, install RStan-ARM and then you install the code from GitHub. But, and they kept saying, oh yeah, we're going to update it. We're going to do it as part of the next RStan-ARM, extension, but it wasn't happening. And so they basically got back to me and I just had to uninstall some packages, reinstall some others. I had to compile it with our tools, but once I figured out how to do it, it worked all the time and I managed to get it on the company's computers and stuff. But yeah, I think somebody here mentioned that the people are wizards. Maybe it was you actually on the chat boards. Yeah, and they were really, really great because, people really helped me out. So it was really nice.
There wasn't like a regular, I've heard sometimes that like some companies only want to use CRAN stuff, so that sort of thing. That was,
Because this was simulation studies, that was okay. We had to run this stuff using a CRO to press the button for us because of that. So, because the CRO didn't have the same constraints.
What is a CRO?
A contract research organization that we were working with, literally I sent them the code and they pressed the button because that was the only way we got around the whole, proprietary stuff. So, obviously still a lot of work to do, but at least we were trying to overcome challenges and everything. So I don't advocate that method but, I think that's just what we had to do. We're just pragmatic and it was the method we wanted to use. So, yeah, and that's it.
One last question.
Yes, I just wanted to clarify. So this is presumably being done in an entirely kind of exploratory way and very much not actually being used in kind of patient context yet.
Has been used in patient context, but I can't present the data.
But the same package has been used in the patient context directly for...
It has. So this package has actually already been done in several papers, in several peer-reviewed papers. If that's what your question is, it was done in an oncology, sort of surgical oncology paper. I don't have the citation on hand, but it has been used.
Okay, I guess I was just following up on the regulatory side of things. I was interested to know exactly what